Right, well, welcome everybody. We're here to discuss one of the latest enhancements done to the Cisco NCS 5500 platform, and in particular what it has to do with the enhanced label stacking imposition. I'm here with a co-worker of mine, Anup.
Hi, I'm Anup. I work with the service provider group. I'm a tech lead, and I handle the L3 forwarding area for NCS 5500.
Great. My name is Jose Liste. I am a technical marketing engineer working also in the service provider business unit organization. And my day-to-day job is working on segment routing and helping customers implement segment routing. So let's get started. The issue of, or the topic of label stack imposition is very important as customers are trying to do segment routing traffic engineering. They realize scenarios where they need to impose more labels than what perhaps the platform can do. So being able to do more with an existing ASIC is very important, and it is a very common request by customers. So why don't we get started by describing what is the current situation if we pick a platform like the NCS 5500 regarding the ASIC and the label stacking position, Anup?
As most of you know, NCS 5500 uses the Jericho platform from Broadcom. So this ASIC can push 6 labels by default. So this is how it does it. So in general, for those of you know, like when the forwarding lookup happens, it gives us a FEC, which gives us the MPLS endcap, and this is basically an object that stores the labels. So when we want to push 6 labels, we basically point to 2 endcaps which are kind of chained together, like we are showing here. So you have the endcap 1, and it points to an endcap 2, and which points to the ARP. So the pipeline will basically read this data and push 6 labels onto the stack, and the packet is going to look like this. You have the payload, and you have 6 labels that are going to be sent out.
So Anup, in this case, I think you're describing a case where we have transport only.
Yeah,
there is
so
no VPN.
Yeah, this example is only for like IP traffic, native IP traffic over the policy. So this gives us the maximum number of labels we can push.
Now, for those that are not really familiar with FEC and endcaps, we actually put a note in here. So here is the egress pipeline, and you can comment and maybe clarify how many labels can you push for each MPLS endcap?
So in one MPLS endcap, we can push 2 labels, and there's a special way you can push the third. So each endcap can push 3 labels.
Total.
Totally. So, and we can link 2 together, and we'll get a total of 6. So that's the maximum that the ASIC supports today.
All right, so then we move on and we look at the case where obviously people are trying to make money out of the network.
Yes.
So they have services.
Exactly. Yeah, so here again, like we saw in the previous slide, we just have 2 endcaps. It's just that in this case, one endcap has the services. These services could be like EVPN or L3 VPN. And as we show here, in this case, the lookup is going to give us the service FEC, which basically points to the service labels. And in this example, we have 2 service labels. And the service FEC again points to the transport, which is basically how the packet goes over the core. And this transport has 3 labels, which is so in this case, we might say that why we can't push 6 labels, it's because of an ASIC limitation. So we can only push 2 service labels and 3 transport labels.
Right.
So the final packet is going to look like this. You have the payload, you have up to 2 service labels, and then you have the 3 transport labels.
Okay, so that's why it's very common to hear from Cisco in our responses that, hey, we support 5 labels when you're doing transport only, or 3 labels plus service when you're doing transport and services. All right, well, so obviously, this actually works very well for many customers, but there are real scenarios, and we will discuss them later in the demonstration, of that people may need to push more labels than is actually allowed within the budget. So we needed to have a solution, and we are here to describe it.
Exactly.
So let's do it.
So now we're staying with the same limitation of 6 labels, but what we are trying to do is like a 2-pass approach. So now the packet kind of takes 2 passes through the pipeline, and so again, if we start, we again do the forwarding lookup for the IP route. In this case, again, like we looked at earlier, this example is for only IP traffic. So the IP traffic is going to give us the transport FEC, which now points to 2 endcaps, the same way it did before. So endcap 1 has 3 labels, endcap 2 has 2 labels, and there's this recycle label as well instead of the 6th label, right? So now this and now we point this to a recycle entry. So what this means is that the packet is now going to take a 2nd pass through the pipeline, and in the 2nd pass, we're now going to use this recycle label and swap it with 1 more label, and then push the remaining 6. So now totally the packet has taken 2 passes, and we had like 2 FECs used, but totally we can now push 12 labels.
Right, so now you have mentioned 2 keywords here, pass 1, pass 2, and recycle.
Yeah.
What is the ultimate impact on the ASIC when this occurs? Is it always impacting or only in some cases?
So it's not going to impact all the time. Only the traffic that is taking this path, based on the PPS and all, will be taking a hit. So we don't expect that all traffic is going to take this path. I don't think that there will be too many 12 label policies in the network. So we might require more for some specific use cases, for like protection and other cases where you might need the special cases.
And that's exactly what we're going to show. We're going to show cases where the dual pass is required, for example, in a very short amount of time, for example, in the case of protection.
Yeah, and there might be some use cases where customers are only looking for a specific kind of traffic stream without the bandwidth requirements. So they might be okay with these kind of use cases.
All right.
So let's look at this example with the service.
With the services now.
So similar to what we saw earlier, we still have 2 endcaps, and now we have the service endcap and the service FEC. So now the packet lookup gives us the service FEC, which has 2 labels. And now the MPLS endcap 2, which is from the transport FEC, is giving us only 2 labels and the recycle label, because we could only push 3 labels in one endcap that we saw earlier. So we have the MPLS endcap 2 with 3 labels and the recycle label, which is pointing to the recycle. So now again the packet comes back to pass 2. So now the recycle label is swapped with another label, and then we push another 6 labels.
So the end result?
In the end result, we have 2 service labels and we have up to 9 transport labels, which is still quite a lot. So we can get totally 9 transport labels.
Perfect. So then this is the new functionality. By the way, is this functionality shipping or going to ship? What are
this is starting shipping from XR7, which is
701 in particular. So it is actually a shipping functionality. The release is out. Well, so the idea now is, after explaining the concept, we really want to put that concept into use with a real use case from one of our customers in Europe. Let's explain the use case.
Sure.
We'll probably start with a picture that shows a segment routing network underneath. I'm running segment routing MPLS. On the top, you will see multiple building blocks. So we're going to describe them. You have the Cisco path computation function, or called the segment routing path computation element. We're going to talk about NSO for service orchestration. We're going to talk about an application called Cisco Crosswork Optimization Engine. So we'll look at the flow. Well, this is actually a very critical slide, Anup. So what we're going to do is describe a real use case that is very common for network operators. I have a provider that has a network like the one displayed before. We now reveal some names. We will use names in our examples. The ultimate goal of the use case is to provide 2 point-to-point services from site A. We're going to call node 10 and 6 on site A, and nodes 2 and 4 as site B. It's going to be a EVC, a point-to-point service going from node 10 to 2. And it's going to be a second EVC between the sites, but this time between 6 and 4. The customer is actually deciding to use EVPN for this signaling of the E-line service. So we're going to use EVPN BPWS. That's fine. So we can create the 2 services. Now, the key is that these 2 services will be carried over a LSP using segment routing traffic engineering, where the LSP that carries the first service I highlighted before and the LSP that carries the second service have to be disjoint. It's very important, especially if you think that this service connects maybe to a cell site router that is bringing connectivity to the mobile operator backbone in here, is that the mobile backhaul provider offers disjointness. So if there is a failure in one of the links, the failure will not have an impact on both services together. So the LSPs that carry service number 1 and the LSP that carries service number 2 have to be disjoint. There are many types of disjointness that one could request from a path computation device. The one that we're going to highlight is one that we call SRLG disjointness. SRLG disjointness actually is a very powerful construct that basically means the 2 paths cannot share any link, and they cannot even share links that have the same SRLG. Okay? So to simplify that sequence or that workflow in our topology, we have actually configured a common SRLG on the uplink, one of the uplink nodes on node 10 and one of the uplink nodes on node 6. I put that in red. Then I have another SRLG that is common for the uplink between 2 and 3 and between the uplink between 2 and 4. So you will see how it works, but basically I want my LSPs to go from left to right between 10 and 2 and 6 and 4 to be disjoint, not sharing any links of the same SRLG, and the same for the other direction. In addition, we have also configured another SRLG I put here in purple on the two uplinks between 10 and 8. The key thing here now is because in addition to having LSPs that are disjoint, I want to enable TI-LFA on my SRT head end. And I want to be able to have TI-LFA where the router performs what we call local SRLG protection, where a primary and a backup path cannot share the same SRLG. So we're building ultimately what is a very rich, a very complex use case that is common for our customers. LSP disjointness based on SRLG and TI-LFA based on local SRLG. Okay? So Anup, let's first take a look at how the whole workflow gets started. We described that we want to have these two services. How are we going to configure the services? We're going to use Cisco's NSO, Network Services Orchestrator. Very popular with service providers and in general operators. I can automate the service provisioning very easily. So with NSO, we're going to see how NSO can be used to program the service on the edge devices, routers 10, 6, 2, and 4. By the way, we didn't emphasize before, router 10 is really the key device under test in this demonstration. Device 10 is the NCS 5500 that has the functionality for the enhanced label stack support. Okay, so why don't we go to NSO and experience how simple it is to configure the service that we just explained. Okay, so we are looking at the NSO in the screen. This NSO instance, as we can look at the device manager, is actually managing the devices that we mentioned, that we showed earlier in the topology. But we are here to configure services on this network. So we come back to NSO, and we have a customized service template to configure the service type that we explained earlier. So we're going to go, everything in NSO is model-based. So we look at our services model. In the services model, we have many ones that we have customized, in particular one that we call ODN layer 2 disjoint. We'll talk about ODN later, but the L2 disjointness is a good hint for us here. So we're going to add a service. We're going to call that service test. Well, the service is beginning to be born. We're going to click on the service, and we're going to do all the attributes of the service, beginning from the type of disjointness. We explained disjointness type. There are many types of disjointness. The one that we are going to execute today is what we call the SRLG disjointness. We're going to also choose a optimization type. I can optimize for the IGP metric. I can optimize for the T metric. As an example, let's pick IGP. All right. Remember my example? So I'm going to actually add a site. So we're going to add a site, let's say on the West Coast. Let's call that San Jose. And then we can add another site. It will be on the East Coast. Let's call that New York City. As we explained in the use case, each site will have two routers. So we can now add a node on a site. This is going to be node number 1 on site New York. So we're on the East Coast. And I can add a router number 2 also for the New York site. Now, this is just the site reference. We need to populate that entry. So my node number 1 will be my router number 2. Then I can pick a VLAN that I want to receive traffic from my customer. We just use one VLAN across our service, 3499. I have a Gigi port 003. So I selected. So I'm done with New York's node number 1. Come back to New York and now configure node number 2. Only my device number 4, the same VLAN. And I'm going to pick my port, Gigi. It's going to be Gigi 001. Okay, we're done with New York. So we're halfway done. Now we're going to configure San Jose. Okay. San Jose, I can add also two routers. I'm going to do my router number 1. Now here's the DUT. So that's my device number 10, if you remember.
Right. Yeah.
Okay? I'm going to use the same VLAN on both coasts, but obviously this is orthogonal to this demo. I'm going to pick our Gigi interface 00039. Right, almost there, and oop.
Yeah.
One more router to go. Remember, we're configuring two EVCs,
two EVCs.
with LSPs that will actually explain how they come up. So it's actually a pretty involved setup. So we're gonna go to node number 2 in San Jose. That will be my router called node 6. Again, the same VLAN. This time I have a 10 gig interface. 03008. Okay, we're almost there. So come back to my service test. I have the 2 sites with the 2 nodes each. I have the disjointness type that I want, the optimization metric. In NSO, we have a 2-stage commit. So we go into the prepare state, and we click on our commit manager. And here we start to see prepare the configuration that we are about to commit. It's not being pushed in this stage. So we commit the prepare state. All right. So that went through, no errors. We come back to now the service. Now we see a service called test. We're going to edit that service one more time. We're going to change the state from prepared to active. And now when we do the commit this time, it's going to push down through the devices. Okay. So now NSO is actually about to push a whole lot of configuration for these 4 nodes. In particular, you can see here in the native config, you can observe all the config that is being pushed down for the 4 nodes in the topology. This is pretty much service configuration that is being pushed, okay? All right, so we go ahead and commit it. This time it will go down for real.
Okay.
Right, we wait for the moving dots to stop moving. All right, no errors. The config made it through. We're going to come back in a moment to the routers to actually see that in action. But the fact is we have now pushed the config of these 2 EVCs. So we left off from the previous slide where we have NSO about to push config. The config has been pushed already. Now we have the PCE. What I'm going to explain here is a very important concept in SRTE that we call on-demand next hop. What is happening from the previous case is we have deployed configuration on the PEs. The routers, obviously, with EVPN are going to exchange service routes via BGP. So there are BGP updates that I'm showing from right to left. Obviously, they're also happening on the other side. At the moment that we dropped the service configuration with NSO, we're also adding a color to these communities. So let's say color 10,000. Color 10,000. Color 10,000 will represent the intent in the network where these routers 10 and 6, when they see a route with color 10,000, they know that they need to request for LSP disjointness for the service routes that came with that color. So color 10,000 is an intent. The intent translates to disjointness. So color 10,000 equals disjointness, and then I need to have the PCE as the one that will compute. So these 2 routers will actually ask the PCE, can you please compute LSPs that are disjoint, and by using SRLG disjointness as an example for the disjoint computation. Okay, so the same is happening for the routes that are coming from left to right, and 2 and 4 are also asking for disjointness for the LSPs coming in the reverse direction.
So how does this sr-pce actually know this entire topology? Is there a different mechanism?
Yeah, in fact, let me clear up the picture here. Obviously, for him to be able to compute, he needs to have a database with the topology. The sr-pce can learn topology by one method is he can be part of the IGP itself that he's connecting to the network, or he can also be he can receive a BGP feed based on the link state address family. So with BGP-LS, he can learn all the devices and the links that are present in the topology. Therefore, he can feed the topology database and then proceed to compute.
So even the SRLG info is exported?
Oh, in fact, all of the attributes of the links, like the different metrics, including the delay, the SRLGs, the link admin groups or the affinities will be fed through BGPLS or by being part of the IGP into the topology database of the sr-pce. So it's a very rich construct, and as we just went over, this is just standard IGP or BGPLS. Okay. All right. So we have that was a very good question. So we have the topology. We have received the computation request. The algorithms that compute the disjointness are here. The sr-pce is basically, for those of you who have never heard of it, it's an iOS XR router. It can be a virtual router, it can be a physical router. So once he computes, let's say he computes paths for LSP1 and LSP2, he returned the path by using PCEP. By the way, the request in the previous error was based on the PCEP protocol, Path Computation Element Protocol. So he will reply with the paths to these devices. These devices will get it, and now they will go to their FIB, the forwarding information base, and they will program a segment routing policy. Segment routing policy will be represented by a seed list that includes a number of labels. So label 1, label 2, label 3. And likewise for the other LSP. That's basically what has happened ultimately in the forwarding of the head ends. Okay. These policies that I show here in blue were only instantiated because previously I received BGP EVPN routes with color 10,000. The whole process of instantiating a policy on demand because I receive a service route with an intent that I was expecting is what we call on-demand next hop, or SR-ODN. Okay, so now we have done 50% of the job. The other part of the job is now I start to receive traffic on the attachment circuit of these EVPN BPWS services, and with another functionality called segment routing automated steering. Any traffic received for a remote prefix, in this case it's an Ethernet segment for EVPN, is automatically tied to the policy in the forwarding. That tie-in is what we call automated steering. The service provider does not have to come to the ingress router and configure anything to make the connection. The connection is automatic because of the intent of the route. Okay, so that's segment routing ODN and automated steering. So at the end of the day, we have triggered two LSPs going in each direction that they are computed by the PCE to be SRLG disjoint. Okay. Now, at this point, we have been talking for 5 minutes, and we have to show that, right?
Yeah.
Okay, so from the previous slide, we came to have the LSPs with the path computed and signaled down to the head ends and installed into the FIB. Now, based on the PCEP protocol, the routers will start to report the LSPs to the sr-pce, again, using PCEP. This is the report message. At this point, he is aware not only of the topology database that Anup, you asked earlier, I also have an LSP database. So I have topo and I have LSP. Here now, for the first time in the demo, we are showing the Cisco Crosswalk Optimization Engine. This is an application that sits on top of the sr-pce. We actually use a REST API. And one of the critical things that it will do, it will actually subscribe to the topology that is present on the sr-pce. So any changes on the physical topology or the LSP topology will be updated through the API to Crosswalk Optimization Engine. Then, obviously here, we have a user that is going to be able to visualize and display the LSPs and the nodes in the network. So I think with this, why don't we take a look at Optima? For those of you who have not seen Optima before, Optima is a Cisco product that has been already released and is ready for deployment. Okay, so let's actually have a look at Optima. We are looking at the browser here. As you can see on the right-hand side, we're displaying the same topology you saw throughout this presentation. So these are my different nodes. I can actually zoom in into a node and get information about the node, the T router ID, ISIS system, the location, of course. I can actually get information about the links on that node, and I can see interfaces with identifiers, and We can even collect traffic statistics on those links and report that. The information on a link will include things from segment routing, such as the adjacency seeds. We can see, we mentioned the utilization, but also pay attention, we have the metrics on the link, IGP, TE, delay. We can also learn the admin groups or the affinity values that are present, that are advertised through BGPLS for the node.
So we can look at node 10 also. That's our DUT.
Yeah, that's our DUT. So that's our NCS 5500.
Yeah.
So our 5500, as part of this demo, is there. And obviously, he's got also a number of interfaces connected to it. And we will see what happens to those interfaces when we start doing traffic engineering. I think most important point is also the panel that we have here on the right-hand side. You didn't have a chance to experience at the very beginning there were no policies. In fact, there were non-policies because there was no service. Remind me at the end to remove the service so we can see them all disappear. That will be our proof. So here we have four policies that are actually going from node 10 to node 2, from node 6 to node 4, and the other direction. Yeah. Here now, we need to use Optima. We can use Optima to see the disjointness. So let's have a look. I have a policy that goes from node 10 to node 2, and we can see that it actually takes a pretty much a crooked path through the network. In that path, the router number 10, our DUT actually has to impose a number of labels to accomplish that. If we go here down this list, we can see the labels. The first segment is an adjacency seed on the head end that points to a local interface. Then we have a node seed of going to 7, and then we have another node seed of going to 1, and then my last seed is an adjacency seed to go from 1 to 2. Right. We show that small dot there. Effectively, on the router, we will have to push 3 labels, 1, 2, 3. The first one here, this dot, is a pop, so it doesn't have to be programmed. But can we really prove the disjointness has been obtained? Well, yes, if we can select the 2 LSPs on the direction that have to be disjoint, I browse over the first LSP. Here's the one that I just described from my DUT, and here's the second one from the second router to the other router on the site in New York. They do not share sr-lg, they do not share any links in general. In the reverse direction, I also have the disjointness. Here's from node 2 to node 10, and from node 4 to node 6. And again, mouse over, first LSP highlighted, second LSP highlighted. They do not share any link, they do not share any sr-lg in the network. I think with this, it's probably good to actually go down to the router. So let's go to router number 10 and show, in particular, the policy that we started with, with the 3 labels. So here we are in router number 10. Actually, in this first phase of the demonstration, we are using router number 10 with an iOS XR release prior to 7.0.1. So we're going to show you the before and the after. So we have a segment routing policy for a particular color that represented the intent. I used the example of 10,000, and here we can see the path that was computed by whom? By the PCE. Is the address 11.1.207, and we have 4 segments in the policy that I explained with the GUI. Now you can see them on the router. Remember, the first one is a POP. Well, we can actually take a look at the forwarding information for that policy. So we can see here that I have my primary exit interface will be this particular interface, GG002, with the 3 labels that I have in my path. Remember, the first label was a POP. So these are my remaining 3 labels. You can also see what I explained earlier. We are enabling TI-LFA in the head end. So with TI-LFA, we can protect, we can have a backup path to protect failure of the first segment of the policy and get 50 millisecond protection. Here is where we start to see, with the local sr-lg protection for sr-lg, we can see that the forwarding entry for the protection of the first segment now requires 4 labels. And this, based on was explained earlier by Anup, now is going to exceed the budget of the ASIC. I have now 4 labels for transport, and then I have 1 or 2 labels for my EVPN.
Yep.
I could not do more than 3 plus the service.
Exactly.
In this case. So this is a representation of what would have happened, something that is not possible to program in the ASIC. So the consequences will be good to see the consequences. So what we wanted to do now is actually create a link failure. So what we're going to do is we're going to come to the node 8, and we're going to fail the primary interface where the policy goes out as, which is my second link between 8 and 10. Okay, so here we are looking at a traffic generation application where we're sending traffic in all the 4 directions. The direction of concern here is the direction of the traffic from node 10 to node 2. Right. As you can see, we're sending 1,000 packets per second with no loss at the moment. This is traversing over the EVP and VPWS over the SRTE policy that I mentioned earlier. What we're going to do is we're going to, as I said earlier, we're going to go to the router number 8 and create a failure of the interface Gigi 0307. That's my interface connecting to node 10 where the policy is going out as. We're going to create a failure. Commit interface went down. We can actually go back to the remote desktop and take a look at the number of frames lost. Well, here we have actually lost around 2,600 packets. That is at 1,000 PPS, that's approximately 2.5 seconds worth of traffic loss. So basically, the fact that we had a backup path, at least pre-computed in the control plane, it never made it into the data plane. So, so the traffic loss.
Yeah, we could not support the TILFA in this case because of the ASIC
enough budget in the
ASIC.
But actually, it will be interesting as we go back to Optima, we can see that the PCE has re-optimized the path, but nevertheless, there was no fast protection provided at the head end. So with that, I think it will be very interesting to see what happens when Node 10 actually is running the iOS XR 701 that has this new feature. So let's go ahead and take a moment. We upgrade the routers and we'll come back. Okay, so we're back. We have upgraded the router to run iOS XR 701. So let's take a quick look. So in fact, 701, and now we want to see what may have changed on the router, specifically to what you explained earlier, Anup, for the enhanced label stacking position. Remember the scenario of the policy. So now we're going to take a look, and in fact, we'll see that we have the policy with 4 labels as shown before. The first label is a pop, so it's really 3 labels in the primary. The interesting one is to take a look at what's happening with the forwarding configuration or the programming of the policy. Well, like it was shown the case before, now I still have my 4 labels for including the protection for the first segment of the failure, and this time with the recycle we do have.
Yeah, we should be able to support this, so we can look at.
Okay, so then let's take a look at the router deeper to look at the forwarding chain. That will be, we're going to do a detail. By the way, we're using aliases to avoid typing a lot, so you will understand that. And here what we can see, actually maybe, Anup, you may want to explain what's going on.
So we saw from the segment routing output that the backup path actually has 4 labels. And the primary path has 3 labels, so we can see the 3 labels here. And in the backup, we actually see 3 labels, but this is not the same label stack that we saw from the control plane, because here we have now split this to support the recycle, because we want to support this stack, right? In the previous case, all 4 labels, we would not be able to support that. So now here, we are going to download only 3 labels, which we can support. And the third label is going to be the recycle label, which will come, which we can look at again, which will then point to the actual egress interface.
So here we're looking at the first pass.
Yes, here we're looking at the first pass.
All right. So then why don't we take a look at what's going to happen on the second pass?
Yeah. So here.
So the recycle label, as you mentioned, is 80,014.
80,014. Yes.
Let's see what happened there.
Yeah, so here we can see the other two labels in the policy. So this is going to be the 80,014 is going to be swapped with 16,008, and the other label is also going to be pushed. And now we point to the actual egress interface. So in the second pass, we're going to go send the packet out correctly.
All right. So
here's
very
right now
important.
The packet is going to go out with the correct stack.
Right. So here's very important. We're using the enhanced label stack solution for allowing the configuration of the backup of the SRT policy at the head end.
Yes.
All right. Well, so now we just try to repeat the same
we
test.
can try it again.
So let's go back. We take a look at our traffic generator. So we're sending packet. We're receiving traffic at 1,000 pps. No traffic loss being reported. We go back to the node number 8, and we're going to fail the same interface as we failed in the previous test. This Gigi 0307. So now we're going to shut down this interface. All right, and we come back to the traffic generator, and we take a look at how many packets we lost.
We just lost 12 packets.
12 packets, which equates at that rate?
10 milliseconds.
Yeah, around 10 to 12 milliseconds.
Yes,
so
10 or 12 milliseconds.
We saw a huge improvement now. The hardware is able to program the backup, and it's activated in a sub 50 millisecond basis.
And the backup path with the recycle has only been active for a small amount of time, so we don't really see any throughput impact or anything.
On the ASIC.
On the ASIC, yes.
Very good. So the feature seems to be working. Right. So actually, to fulfill our promise, I think because people didn't see the policies coming online on demand, let's actually remove the service and see how everything disappears. So we take a moment and go back to NSO. Okay, so we're back in NSO. We come back to the service manager. Remember, I had our service test, and we are going to remove that service. Actually, I should have done it back from my model browser interface. I click on services, and I have my service test. I can now go ahead and delete the service. All right, the service is now ready to be committed. I go to my NSO commit manager. Okay, so here. So now we're going to commit for good the deletion of the service. So we do one last commit. We're waiting for the operation to perform and remove the service. Now, what's going to happen here is that as you remove the service, you're removing the routes that carry the intent. When the intent is no longer there, then the routers will remove the forwarding information from the SR policies on their databases. So the commit went through. Now, the most important way to actually take a look at that is to go back to optimization engine, and we take a look at the topology. We do a quick refresh, and now there are no policies.
Okay.
All the LSPs are gone. Why are they gone? Because there is no more service. There is no intent, and there is no service. Then there is no need to have the policy. Obviously, we can take a quick look at the router. Let's go to our head end, router number 10, and if we do our commands to look for the policy for color 10,000 is not there. Okay. So the policy is gone, the state is gone, everything is gone. So with this, actually, we have demonstrated this very specific, very important feature to enhance the label stack on platforms that otherwise will have limitations.
This is a very useful use case, right? I mean, without this, we were not able to support proper TILFA for SR policies.
Well, so service providers can now engage on having more sophisticated SLAs for their customers, like SRLG disjoiners, and highly availability with the TILFA at the SRT head end. Well, Anup, if people want to get more information, please refer to the blog entry that is companion document to this. We will we include all the show commands and anything configuration-wise and verification steps for what happened on that NCS 5500. And with that, we wanted to thank you for your time. I want to thank the audience for joining us, and we hope that this blog and this video in particular is of interest to your companies. Enjoy.
Yeah, thank you.